All right, so basic concepts for 1.3 is that a function is a process or computation that receives inputs and outputs, right? So you put something in, you're gonna get something out. The most applicable examples of a function is a vending machine, right? If I put in a code into the vending machine, I'm gonna get something out for that specific code. Does that make sense? All right, that's an example of an input and output situation. Okay, so a verbal, real, natural situation is here. Although thunder is caused by lightning, we can sometimes see a flash of lightning before we hear the thunder, right? The further away the lightning is, the greater the time lapse between the seeing the flash and lightning and hearing the thunder. There's an input and output situation right there. It may not necessarily be a function, but there is a relation between thunder and lightning. Does that make sense? All right, so given that in our minds, if you look right here, this table was created and it's approximating the distance in miles between a person and a bolt of lightning when there is a time of lapse, okay? Seconds from lightning and hearing the thunder. So for example, 5 seconds of lapse in time means that it's about 1 mile away. 10 seconds of lapse in time means it's about 2 miles away. 15 seconds of lapse in time means that it's about 3 miles away. Does that make sense? So this represents a function. So if I hear the sound, I wait 5 seconds, that lets me know that my output is 1 mile away. If I hear the sound, I wait 10 seconds before I hear another sound, then that lets me know that my output is 2 miles away, okay? So the function is computing the distance between the sound and the lightning bolts. Pretty straightforward example, right? Questions about verbal or table example of a function right now? Cool. All right, function machine. Do y'all remember seeing this in the Algebra 1 class at some point? Okay, the function machine is basically a visual representation of something going in, AKA your input, which we call X, your function, processing it, which we call your F, and then your output, your F of X, which is also your Y, okay? All right, the difference is that when you're using function notation, you use F of X instead of Y. Okay, function notation. Function notation literally means that instead of Y, we use F of X. And that's because we're stating the name of our function and we can see what's being input into the function, okay? But F of X clearly does what? Equals Y. They're the same thing. I like to say it's Y all dressed up. It's the fancy Y. Okay. Questions about function notation? And again, for your notes, it's your notes. So what you're taking as notes is information that you may feel like you need. Remember, all of our notes are available on your Brightspace. So if it's something you like, oh, I didn't get to write that down, remember, you can go back to your Brightspace, go to the week that we're on, click on that assignment. All right, domain and range, yay, okay. Our input, that is called our domain. Our output, that is called our range, okay? A function f that computes the height after x seconds of a ball thrown into the air. In this case, domain is our time, right? Time is typically your domain, and our range is the height of the ball, right? So even without seeing a function, without seeing the graph, I know that, can I control time? No, that's what I'm mapping it by. But I can measure what changes over time, okay? So typically your domain, when there's time-related problems, is time, and range is whatever the output or what's occurring at that time. All right, so find the domain and range. Finding the domain and range from function notation. So this is an example of function notation. And so when you're looking at function notation of an ordered pair, it can become written in a less character format. So all you have to do is remember that this is your X, your input, this is your Y, your output. This is your X, your input, this is your Y, your output. X, your input, Y, your output. X, your input, Y, your output, right? So when I write it as an ordered pair, f of -1, 4 becomes -1, 4. Do you remember this? How to go from function notation to ordered pairs? Okay, I'm just going to quickly do it for all of them. So therefore, the function is represented by this set of ordered pairs. Notice when I list out the ordered pairs to be mathematically, grammatically correct, I list in order from least to greatest x value. Okay. Questions so far? Cool. Now, stating the domain and range. When I'm stating the domain and range, again, domain represents my x values and range represents my y values. When I'm listing out the domain and range, I want to be in numerical order. And you do not repeat. So there's no repeats. Typically, but in some weird cases, it does. I don't know why. So here the domain is going to be all of my x values and the range is going to be all of my y values. So here's my set. Notice my domain had no repeating values. My range did, but how many times did I write the 4? Once. Okay. The main times that you would write repeating values in a set is in a statistics class. FYI. Do you feel comfortable going from function notation of an ordered pair and stating the domain and range of the ordered pair? Cool. All right. So formal definition, you don't have to write it down, but just so that you're in the formal definition, a function is a relation in which each element of the domain corresponds to exactly one element in the range, okay? The ordered pairs for a function can be either finite or infinite. Finite is an example of ordered pairs. Infinite is an example of a graph, a continuous graph, which means that it doesn't have a stopping point, right? Okay, basically what this formal definition is saying that your, x values do not repeat. So if I'm a function, what's the main thing? X values do not repeat. My input, my independent variable, whatever you want to call it, does not repeat. Okay. Questions, comments, or concerns? Huh? Cool.